So right now we're going to start section 3.6 and we're going to talk about representations of numbers. Your suggested exercises are going to be 1, 3, 5, and 7. The big ideas are going to be Theorem One, which is just a theorem for this section, and that's going to give us the base B representation of a number. We're also going to deal with binary, octal, decimal, and finally hexadecimal. Right, so here's Theorem 1. Given natural numbers n and b, there exists a unique sequence aj, where j goes from 1 up to k, with all the aj's coming from zb. So this means they're integers between 0 and b, excluding b, so 0, 1, 2, 3, 4, 5, up to b minus 1, such that n equals a sub k b to the k plus a sub k minus 1 b to the k minus 1 plus dot 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 plus a sub 2 b squared plus a sub 1 b to the first power plus a sub 0 b to the 0th power. So of course b to the 0th power is 1 and b to the first power is just b. This is called the base B representation of n. All right, so if b equals 2, we've got binary. If b equals 8, we've got octal. If b equals 10, we have decimal, which is what, the way we normally write numbers. And finally, if b equals 16, we have what we call hexadecimal. All right. Let me do a couple of quick examples that I think will make this make some more sense, and then I'll give you a table that you should memorize, but memorize is kind of in quotes because it's pretty straightforward, and really it should be the kind of thing that you can calculate quickly and or memorize. So let's do some examples. I'm going to say 743 in base 10 is equal to 7 times 100, which is 10 squared, plus 4 times 10 to the first power, plus 3 times 10 to the 0th power. So this is probably not surprising. You look at 743 and probably the first thing you think of is 743. Now let's do another example. Let's look at 743 in base 8. So this is going to be 7 times 8 squared plus 4 times 8 to the first power plus 3 times 8 to the 0th power. Okay? So this little number down here is the base. And if I don't write a base, then we can assume it's 10. But here I'm just emphasizing the 10. Now we could convert this to base 10 just by sort of doing things the way that we would normally. We've got 7 times, 8 squared is 64, plus 4 times 8, that's 32, and then plus 3 times 1, that's 3. So what is 7 times 64? I honestly don't know. 64 times 7, let's go over here. 28, 42, so it's 448 it looks like. So this is going to be 448 plus 35. And so what's 448 plus 35? Again, I don't know. It's going to be a 3, carry a 1. 4 plus 3, so 8. 483 in base 10 is what it looks like to me. So that's how we're going to be converting between bases. I suggest you practice these, especially with binary and hexadecimal for computer science people. The only time that I see octal really that I can remember is for setting flags in some Unix type systems. But I mean, it's probably worth at least being aware that octal exists, but really binary and hexadecimal are going to be the primary things you need to learn from this section. All right, so I want to make a quick table. So decimal because that's what we're probably used to. Binary, wow, that B had a rough day. Binary, octal, and finally hexadecimal. So let's just try to, I want to try to make a nice chart for you here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Fill these in. So these are numbers like we're used to, right? We normally write them. You just assume it's in base 10. So for binary, 0 is 0, 1 is 1, and then 2 is going to be 2 times 1 plus, or 1 times 2 to the first power plus 0 times 2 to the 0th power. 3 is going to be 1 times 2 to the first power plus 1 times 2 to the 0th power. 4 is going to be 1 times 2 squared plus 0 times 2 to the first power plus 0 times 2 to the 0th power, etc. And so we can fill this in. Just all I'm doing is I'm adding 1 each time, but I have to carry, because there's no 2, so I have to carry every time I add 1. Sorry, every time I add 1 and 1. And what some people will often do is they'll fill in these leading zeros here, because each one of these is called a bit. That's short for binary digit, each 1 and 0. And you probably know that a collection of 8 bits is a byte, but you might not know that a collection of 4 bits is called a nibble. N-Y-B-B-L-E, nibble. Okay, an octal, it's going to be just the same as decimal for 0 through 7. 1, 2, 3, 4, 5. That 5 is a little rough. 5, 6, 7. But then since we're in base 8, now we've got 8 to the first power times 1 plus 8 to the 0th power times 0. Then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 1, 7. And I hesitate to say 10 or 13 or 16 or something like that. I like to say 1, 0 because this is in base 8. And 10 makes me think of, you know, the number that's 2 greater than 8. But this is actually 8. It's just represented in base 8, so it's 1, 0. Finally, a hexadecimal, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when we run out of Arabic numerals, we just start using letters. So A is decimal 10, B is decimal 11, C, D, E, and F. So you should learn this chart and be able to reproduce it pretty quickly on your own, especially if you're doing computer science stuff.